So hello and welcome everyone. Hope you are doing well, and today we are going to discuss, yes, it's quite an interesting topic. It's rolling motion. So basically we can divide this part into 5 major categories. So we have pure translation, pure rotation, pure rolling, where we can see both the translation and the rotation, and we have another 2 scenarios, which are when rotation dominates translation and translation dominates rotation. And today in our video we are going to mainly focus on the topic pure rolling. So let's now come to the point. Suppose there is a disk which is executing the pure rolling on the ground, and it is rotating with its angular velocity omega, and the velocity of the center of mass is VCM, and radius of the rotating disk is r. So what is going to be the criteria for it to perform that pure rolling? Now coming to the point, we have the most important criteria, which is the point which is at the contact to the surface should have no relative motion. Yes, the point at the contact to the surface will have no relative motion. That means that VCM will be equals to r into omega. Now what's that? If this disk rotates in this direction, its VCM will act like this on the forward direction, and its r omega will be opposing it on the reverse direction. So both two will have to cancel out each other to fulfill the criteria of no relative motion in the point of contact. So now we have got that VCM equals to r omega is the condition for the disk to execute pure rolling. Now we will take a closer look. What if we differentiate the both sides with respect to time? So you'll get ddt of VCM equals to ddt of r omega. That is, we can take the r out of the differentiation because the radius of the rotating disk doesn't change. We can treat it like a constant. So we have got ddt of VCM equals to r into d omega dt. So we finally get ACM equals to r alpha. Now here ACM is the acceleration of the center of mass of that disk, and alpha is the angular acceleration with which the disk is rotating. So from here you can think that this is another condition which is sufficient to decide and state that the disk is executing pure rolling, but it is not, because if we integrate it now, what we got as the final equation, that ACM equals to r alpha. So integrating both sides, we finally get that integral ACM dt equals to integral r alpha dt. Here again the r comes out, and we get integral of dVCM equals to r integral d omega. That is, at the final equation we get VCM equals to r omega plus c. Yes, here's the important perspective. C, that is the integration constant, comes out. Here the motion can only be pure rolling when c is 0, that is the constant is 0. So we can conclude that only then that equation ACM equals to r alpha will state that the object is performing a pure rolling. That's it's a particular case when the c is 0. So in general we can conclude that ACM equals to r alpha is not a satisfactory condition that we can say the disk is having a pure rolling motion. Similarly, you can think, how about the equation SCM equals to R theta? Now I tell you that this equation SCM equals to R theta definitely suggests a pure rolling motion. But pure rolling motion doesn't necessarily mean that the equation will always be satisfied. That is, if pure rolling occurs, S may or may not be equal to R theta. Let's deduce it mathematically. Suppose we take the equation VCM equals to R omega and again we integrate it. Now VCM equals to R omega. SCM here is the displacement of the center of mass and theta is the angular displacement of the rotating disk. Now integrating, we will get dSCM equals to R d theta. So as a final result, we will get SCM equals to R theta plus C. Here also another integration constant C comes out. So SCM equals to R theta is not the one and only condition for pure rolling. As we can see that SCM equals to R theta plus C, then also the disk will exactly perform the pure rolling motion. So SCM equals to R theta is not the one and only condition. So now, as we have discussed about the conditions of the pure rolling, we are going to do something more interesting now. So now we are going to discuss about the velocities of a point that can be on the circumference or inside the disk at different moments. And also we will unleash the trajectory of the point during the execution of pure rolling motion. So for this we have this setup, and we will introduce here a disk which will have the color green. Yes, you can see the green disk. It will have a radius of 2 units and have omega of 2 units. And as we discussed earlier, that obviously as it is performing pure rolling motion, so V will be obviously equals to R omega, so V will be 4 units here. And this disk is free to perform pure rolling motion to the x-axis. Now we will consider a point on the circumference. Let's take it as a red one. Yes. So we have a arrow here to indicate that point so that you can see the rolling more deeply. And the main thing is that we have to introduce 3 different vectors here to represent 3 different kind of velocity. So we will bring here a maroon vector, which you can say represents the velocity of the center of mass, that is the VCM vector. We will have another one. This will indicate the R omega vector, and we will finally have a black vector here, which will indicate the resultant of those two. Now you have to remember that these lines not only show the direction of the respective vector, but their relative length also gives you the idea about the magnitude of the real vectors. So we are almost ready to make the disk roll. So you can start here. So look how it rotates and rolls to the positive x direction. Again wind this back and you can again see it. Now the most important thing is note when the red point comes at the bottom and becomes the point of the contact to the surface, as we discussed previously, that let's bring it more back again and play. You can see that the R omega and the V vector, that is the maroon and the yellow vector, are opposite to each other and they cancel out each other. So at the point of contact, just like here, the black vector vanishes. That is, there is no relative motion to the point. So we have proved what we previously told here through this graph. So this was about a point on the circumference. Now things are going to be a little bit tricky. What will happen if we take a point which is inside the disk? For this we have first to remove these vectors so that you can understand it more clearly. Just remove this. I'm going to also remove the red point from here, and we instead will take a point, as I said, which will be inside that rotating disk. Let us take it as a blue point. Now the blue point has appeared. I have zoomed the image so you can see it clearly back to its original position. You can see it here. And for again we have to introduce 3 more vectors. Now this will act from this point. We have that maroon vector which implies the VCM vector. We will have the new r omega vector. Now note that r is the distance from the center here, not the radius, because we have taken a point inside. And we will have, as before we had, again a black vector which represents the resultant of these two. And again you can bring this to your primary position and see how it moves. Now see the change the lengths of the vectors. Note that the black vector here never vanishes. It means that for a center which is inside a rotating disk, the point will be never stationary with respect to the ground. Now we are heading to spot the trajectory of the point of the disk as it moves over the surface. So first we will consider the point on the circumference. So we will have to remove this all. So we remove this and we bring the previous point, the red point. Here you can see, if I bring this little bit right, you can see the red point is brought again. And now the curve which the red point will trace will be here, like this, the yellow one. Now here the interesting things comes. As you can see, I rotate the disk about the x-axis, exactly follow the paths which the red points trace. Now look, it has never been detached from that graph, so you can say that it will trace that curve. And this type of curve is known as a cycloidal curve, or you can say simply as a cycloid. You can see it again if we play like this, how it rolls. If you want to see it with vectors, I can also introduce those. Those were the velocity vectors which I am talking about, is this and this. Look how it rotates and rolls over here. Now the interesting fact is that the bottom points of the cycloidal curves, where it has touched the x-axis, look, there are sharp corners. This means that the curve is not differentiable at those points. So we can say that we can have no velocity, or we have no direction of that velocity, because we can't dot tangents there. So from there also we can say that at the point of contact to the surface there will have no velocity, or the velocity will be 0. And now we will move for the curve traced by the point which is inside the disk. For this again we will go to the setup and bring that previous blue point. You can see that blue point has appeared here. I can again zoom out for you. Yes, you can see that. So if the picture becomes a bit exaggerated, I can remove off these vectors here, and I can remove the cycloid too for you, and I can remove that previous red one too. Now the curve which will be traced will be looking like this. Yes, the green one. As you can see, the pure difference between this one and the previous cycloidal curve which we had. The interesting thing is that note that where we had sharp corners for the cycloids, there is no sharp corners. That means the curve is differentiable everywhere. So we can say that for a point inside the rotating disk, the relative velocity with respect to the ground never becomes zero. We can play the video again for you, and you can see how it rotates along the axis and traces the curve like this. I will also bring that yellow cycloidal curve again for you to compare the difference between those two. It will be great to watch, see the difference. These two curves are not the same because the points were different. I can play this again and you can see how the point inside the disk follows that trajectory. But we are not finished yet. If you take a point that is out of the disk so that the distance from the center becomes more than its radius, what we will see, that is, we're talking about the point. Now closely look at that blue point, concentrate on this. We are taking the point outside the radius slowly here. You can see how the slowly changes into this type of curve. Now this is very interesting. It has now gone past the cycloidal curve, and if you want to see with the help of the vectors, I can again bring back those velocity vectors. Those will be this and this, so you can compare now the vectors also. But this kind of trajectory can be seen in real life. Suppose you have a spool that is rolling on a track. Many of you must flown kites, so you will be familiar with this kind of structures. And if the spool rolls on the track like this, the trajectory of the point on the circumference of the large discs at the both sides would be the curve which previously we traced. Yes, the green one. So with the help of the vectors, you can see here, if we play the video, you can also see how the point traces that curve. If we increase that point's distance from the center, the curve will look like this, and as we come closer to radius of the rotating disk, it will just be coincided with that cycloidal curve, and when it comes on the circumference, this curve becomes purely the cycloidal curve. And if we bring that point inside now, we will see that curve which we discussed earlier. Yes, that's the magic, or you can say the magic of physics. So I have here simple questions for you, an easy one. What if we take that point to the center? What would be then its trajectory? If we take that blue point on the center, what will be its trajectory? You can see at various points how it looks like the curve, but what will be the trajectory when it comes to the center? Think a bit more. You can pause the video if you want more time. Do you get it? Yes, it will be a straight line. I can show you, like if we take the point, sincerely follow that blue point as it comes on the center, it becomes a straight line like this, because at the center we have r equals to 0, so r omega b will always equal to 0, and only VCM will be there, so the curve will be straight line. So hope you all enjoyed this graphical representation. Now, as we have completed our discussion about the velocity of different points on a rotating body, whether it be on the circumference or it be an interior point, in a graphical method, now we are going to find out the same thing in a mathematical approach. Now this is going to be real easy. So we have to consider again that rotating disc executing pure rolling motion with radius r and velocity of the center of mass VCM, and the angular velocity will be omega. Now if we take the topmost point P, the velocity of center of mass, that is VCM, will act at the forward direction, and the velocity which is due to rotation, that is r omega, will act on the same line in the forward direction at the topmost point P. Now these two simply add up and becomes VCM plus r omega at the topmost point P. And remembering the principal criteria for an object to execute pure rolling motion, that is its VCM will be equals to r omega, we can substitute either VCM or r omega and write the velocity at point P to be 2 VCM or 2 r omega. So we can see that at the topmost point the velocity becomes double of the velocity of the center of mass. Now similarly, if we go forward to find out the velocity of the bottom point, denoted by Q in this diagram, we can simply apply the same logic. The velocity of center of mass, that is VCM, acts on the same direction as it was acting in the case of topmost point, but in this case the velocity due to rotation, that is r omega, acts at the opposite direction. So simply we can write that the velocity of Q will be equal to VCM minus r omega, and again from that condition which we are telling again and again, that is VCM will be r omega, so these two will cancel out each other, and what we are left with at the end is 0, as we had derived it previously with that graphical method. Here you can say mathematically again, as this will cancel out each other. Now as we are discussing about velocities of different points in a rotating object, here we have a simple example from your daily life. Yes, you can see a bicyclist, and you can see the picture of the rear wheel of a bicycle. Now you have to take note that the upper half of the cycle wheel seems to have blurredness. This is because the spokes are blurred. You can recall from your everyday memory that whenever you capture something like fast moving object or creature, the image becomes somehow, or we can say that it can become blurred to an extent. That same thing had happened here, as when the photographer has clicked the shutter and the cyclist was in quite a good motion, so the upper part of that rotating disc here, that is the rear wheel of the cycle, has blurredness because the spokes on the upper part were moving with relatively larger velocity than the the spokes at the lower part, because the lower spokes can be viewed prominently. As we can see that we gradually move upwards from that wheel, that is the point touching the ground at the grass. As we grow gradually up, we can see that the blurredness increases, and we can conclude that the speed at that point also increases. Now you can find out the link of the original photo from our description, which is given below. Similarly, we can find out the velocity of an arbitrary point on the rotating disk. Let's take that rotating disk again. The velocity of the center of mass is vcm, the radius is r, and angular velocity is omega. Now take that arbitrary point to be t, and if we connect t with the center, it creates an angle of theta. Theta can be anything here, as we are taking an arbitrary point. So it creates an angle theta with the vertical line, or you can say the vertical radius. So for this, again, we have the velocity of center of mass vcm acting at the forward direction from t, and the velocity due to rotation, that is r omega, acting like this, as you can see in the picture. So from simple geometry, you can say that the theta angle also becomes here between the vcm and r omega, and from then you can now simply have formula of vectors, and you can say that vt, that is the net velocity of that point which is at the circumference, is root over of vcm square plus r omega square plus 2 vcm into r omega into cos theta. And you can leave that form like this, or whatever, you can do some more calculations like which we have shown here in the video. You can take that root 2 vcm common out of the root over, and you can also make that 1 plus cos theta into the 2 cos square theta by 2, and you can also simply make 2 vcm cos theta by 2 if you want to express this expression in terms of submultiple angles. That will not matter much. And if we now move to find velocity of an arbitrary point inside the rotating disk, similarly we will take consideration of the same things, that is the rotation will be in omega angular velocity, and radius of the disk remains r. Now the difference is that the distance of that point from the center here becomes smaller, and smaller becomes smaller than capital R, because we are taking consideration of a point which is in the interior part. And for the reason we have chosen an arbitrary point, we will take the angle theta, which is made by the line which is created by the center of the disk and the point T. Similarly, as the previous example which we showed, the angle between VCM here, which also acts on the forward direction, and the R omega, which is due to the rotation, becomes theta from geometry. And again, simple, you can apply the law of vectors and you will get the velocity of t, that is vt, to be equal to vcm square plus r omega square plus 2 vcm r omega into cos theta. So one thing you have to just keep in mind here is that r is here small because the distance from the center of that arbitrary point in the interior of the rotating disc is small r. Now, so far we have made a detailed discussion about the rolling motion, its kinematics, the criteria of pure rolling, velocities of different points, and a lot more. Now we will go ahead and discuss some mathematical problems based on the knowledge we have had so far. So here is an example. Let's take it. So what is said here? Two different ropes are wound around the wheel and the axle of a pulley. Now the rope on the wheel is pulled upward with a constant acceleration of a, and the rope on the axle is pulled downward with a constant acceleration of 3a. If radii of the wheel and axle are 2r and r respectively, Then find the acceleration of the center of mass of the pulley and also its angular acceleration about its axis. Now the statement which is most important here is that friction is enough to prevent slipping. So we can conclude that the rope doesn't slip, that is, friction is enough to prevent slipping. From here we can conclude that we can apply the concepts and formulas of pure rolling in solving the problems. So if we take a closer look at the diagram, if we take alpha like this in this direction and ACM at the downward direction, we can simply write down the equations as here. For the inner circle, we will have ACM plus R alpha will be equals to 3A, and the reason behind it is at the point of contact of the rope to the axle there will be no relative velocity, and for this situation there will be no relative acceleration because the mathematical problem is represented by acceleration here. So from this equation you can just leave it here and again consider the outer pulley. So here we have 2R alpha acting on the upper direction at the point of contact to the rope, and ACM, as we had previously taken ACM downward, it will act at the opposite direction, and the resultant that is given in the problem, that is A. So concluding all the things, we can write here 2R alpha minus ACM will be equal to A, and again the reason being that there will be no relative acceleration at the point of contact with the rope. And now we can simply solve these two equations by adding. We will have 3R alpha will be equal to 4A and alpha will be equal to 4A by 3R, and if you can put the value of alpha here in the equation, and you will have ACM to be eventually 5A by 3. Now if we took the alpha previously at the backward, or you can say the opposite direction, you will get a negative value. So that would mean that the rotation was actually at the opposite direction. So we have another problem here. The cylinder is held between the two horizontal planks. Now the upper and the lower planks start moving with velocities 5v and v in the same direction respectively. The direction of the velocities is as shown in the figure. Now you have to find out the velocity of the center of mass of the cylinder and the angular velocity about its axis. Now again we have told here that the friction between the plate and the cylinder is enough to prevent the slipping. So we can apply the formulas of pure rolling in solving this problem. So again, if we take a closer look, if we take the omega to be like this in this direction and VCM in the forward direction, and if we name the contact to the upper plank to be P and the point of contact to the lower plank to be Q, we can say for point P, as there is no relative velocity, we can simply write down that VCM plus R omega will be equal to 5v, which is the velocity given for the upper plank. And at point Q we can write VCM minus R omega will be equal to V. Simple it's. So we can add this equation once and subtract the equations, and we will have VCM to be equal to 3v and R omega to be equal to 2v. So we will have omega to be equal to 2v by R. So this is how we generally approach this kind of problems. So we have discussed two problems here with you. Now it's your turn. We are giving you three problems which you can try at home, and let's see how many of you can get to the correct answer. You can just simply post your answers in the comment section below. So here are the questions with the diagrams. I'm just going through it once for you. The number one is The given figure shows a system of spheres and planks. The velocities of the planks are given. Find the velocities of the center of mass of the spheres and also their angular velocities. And enough friction is there to prevent the slipping of the surfaces. So you just need to watch the diagram carefully and you can easily solve the problem. Number 2, a sphere is placed between two plates which are parallel to the xy plane as shown in the figure. The upper plate is moving with the velocity 3v along positive x-axis and the lower plate is moving with the velocity 4v along positive y-axis. Find the velocity of center of mass and angular velocity of the sphere in vector form. And here also the friction is enough to prevent the slipping of the surfaces. You can have a closer look at the diagram which is given on the right side. And number 3, in the figure given, the top view of a cylinder between two vertical plates is shown. The component of velocity of one plate along its plane is 4v and that of the second plate is v with respect to the ground frame as shown in the figure. The velocity of center of mass of the cylinder is parallel to the direction of 4v. Find the angular velocity vector of the cylinder about its axis and also find the velocity vectors of the plates and the center of mass of the cylinder with respect to the ground frame. Here also friction is enough between the plates and the cylinder to prevent slipping and the ground is smooth. You can have a close look at the diagram here. And now we are handing over a job to you to think and imagine. You have already known the important conditions and criteria of pure rolling. What you have to do is to think of a simple experiment by which you can conclude whether a rolling object is executing pure rolling motion or not, just by seeing it from outside. That is, you can conclude that whether it is slipping or executing pure rolling motion. Now you can use only things or objects which we come across every day and without using any sophisticated instruments. So let us see what kind of ideas you have, and you can simply describe your experiment setup in the comment section below, and we are hoping for the best of ideas. So this was it. If you like this video, please don't forget to like, share, also subscribe to this channel. You can also give a tap at the bell icon to get notified whenever we appear with fresh new topics. You can also follow our Facebook page, Twitter account, and can also find us on Instagram. You will have regular physics related topics and can also present your queries. The links are in the description below. For this time, it's time to say goodbye and do take care of yourselves.